Well, hello again. In this example, you will learn how to develop shear and moment equations for beams. We're going to take a look at this particular beam. It's got a couple of triangular loads and a uniformly distributed load. I guess compositely you can look at it as a trapezoidal load. But we need to develop the shear and moment equations for each of the three segments, and we want to use the coordinates that have been indicated here. So you'll notice that for the first segment, our origin is there. Second segment, our origin is there. And third segment, we're actually going to come back from the other direction. And we want to then go ahead and develop the equations for that. Let's go ahead and start with the very first segment. And so the process that one takes is that you then cut somewhere within that segment. Let's make sure this is clear for you. This is segment 1. This is segment 2. And this is segment 3. So we're making a cut within segment number 1. And the distance we cut is a distance of x. And so this is the free body diagram that we've got going here. And this is the dimension right here that we cut, a distance of x into that. Now what you're going to notice is we do have a triangular load on this. We also have some unknown internal forces. So I'm just going to label those as V1 and M1 because we made a cut within segment 1. We also need to sketch a resultant here for the distributed load, and since it's triangular, it is located a third of the distance here, so x1 divided by 3. Now in order to get the resultant, we can do that easy enough if we knew what the magnitude of this triangle right there was. I'm just going to write a couple of question marks. What is the magnitude of that right there? Well, in order to do that, we actually need an equation for the triangular load. Let me just go ahead and write that out here. We need equation. I'm going to abbreviate that with EQN for the triangular load. The way we're going to look at that is just recognize that you're trying to describe the line here. Let me draw the line here in red. You're trying to describe that line, and so we look at this simply as a slope. And we know that the rise on that triangle is 700, and the run on that is 7. So it's a rise. The magnitude of that triangle is 700 PLF. The run on that is 7 feet. And so we just use slope-intercept form. So W as a function of x1 is the rise, 700 pounds per linear foot over the run, 7 feet, multiplied by x1, so that's slope times x, plus the intercept. But notice right here where x is equal to 0, the load is 0 there as well. So it'd be a plus 0 there. So we can then write this load equation as 100 x1. If I bring this back, then I can use this, and we can then find what the magnitude of that resultant load is. We'll just take 100 x1 multiplied by the horizontal dimension x1 times 1/2, and that will then be equal to 50 x1 squared. Let's go ahead and write that up here. 50 x1 squared. Now that we've got a complete free body diagram, we can go ahead and use equilibrium equations to solve for this. So some forces in the y, 6650 minus 50x1 squared minus v1 is equal to 0. Now I've used that abbreviation v1, but when I actually solve for it, I'm going to write it just a little bit differently here. I'm going to call it v as a function of x1 is equal to negative 50 x1 squared plus 6650. Now, an equation, whether for shear or for moment, is not complete unless it actually has the valid domain for the value of x1. So let's take a look back here, and you will quickly note that segment 1 has a valid domain from 0 to 7 feet. So let's go ahead and write that. And the reason I didn't write this right here as an equals is simply to acknowledge the fact that we can transition at that point where the load changes. So I'm going to just take that off here again. Okay, but we do need to finish that out. We will do that by summing the moments. So I will sum moments. I'm going to do that about the cut. My recommendation is that you always do it about the cut. It'll help alleviate mistakes for you in the future. So that'll be negative 6650 pounds multiplied by the moment arm x1 plus 50 x1 squared times its moment arm of x1 over 3 plus m1, and all that quantity is equal to 0. So from that we can get that the moment as a function of x1 is equal to negative 50 x1 cubed over 3 plus 6650 x1. And that's going to have that same valid domain that we talked about before, valid between 0 and 7 feet. Okay, so that's segment 1. Let's talk about segment 2. We need to make a cut somewhere out in segment 2 and do a free body diagram from that. So here's the free body diagram we would get. Now this is the dimension right here of x2. So let's go ahead and sketch our unknown internals. So our unknown shear and moment. I assume positive directions for those. Segment number 2. And then we need to go ahead and solve for the resultants so that we can complete the free body diagram. So for that triangular load, the resultant there is 2,450 pounds. And all I did was I took this intensity right there, which was 700 PLF. So it's 1/2 700 PLF times 7 feet. And that was where you will get that 2,450 pounds. Okay, let me unclutter this drawing just a little bit, and let's get a resultant for that distributor load. So this one's going to be 700 multiplied by the distance over which it acts. That's that x2. Then we need to get a couple of moment arms here. So that distance there is x2 over 2. And I don't know, you may run into a little bit of difficulty coming up with this one. But let's just kind of break this down. We know that it's going to be a distance of x2 plus 1/3 of the distance of that triangle. So plus 7 over 3. Once I get that, I do have a complete free body diagram, so let's begin running our equilibrium equations. Sum of forces in the y. And with that, we can then go ahead and write that shear as a function of x2 is equal to negative 700 x2 plus 4,200. We want the valid domain for this, so look back at your original sketch. Valid domain, remember x starts right here and goes on, and so it is valid for a total of 12 feet. So we'll go ahead and get that sketched in there. So 0 to 12 feet. While we're here, let's go ahead and get the moment equation. So, as I recommended before, some moments about the cut that you made. So you get negative 6650 pounds multiplied by x 2 plus 7 feet. Then you're going to have plus 2450 pounds, and that'll be multiplied by its moment arm of x2 plus 7/3 feet plus 700 x2 multiplied by its arm of x over 2 plus m2, and of course all that is equal to 0. And so m, as a function of x2, we just do some algebra on this, get it all worked out. Negative 350 x2 squared plus 4200 x2 plus 4833. And that is valid over that same domain that the shear equation was, of 0 to 12 feet. Let's go ahead and wrap this up by looking at our final segment. I'm going to make a cut somewhere in segment 3. Now you can go ahead and use the left section once you've made that cut, but we'll find it's going to be much easier for us if we use the right section, mainly because we've already got some of the information here, such as we know that the equation for the load is that 100x, and so we can go ahead and get our resultant sketched in here. So that's that 50 x3 squared, and our unknown shears. So V3, M3, we know the distance here is the distance of x3, and that this dimension right there is x3 over 3. Equilibrium equation, some forces in the y. V3 minus 50 x3 squared plus 6650 pounds equals 0. So V as a function of x3 is equal to 50 x3 squared minus 6650. And that will be valid on the domain of 0 to 7 feet. And then we can some moments about the cut. Negative m3 minus 50 x3 squared times its moment arm x3 over 3 plus 6,650 pounds times x3 is equal to 0. So moment as a function of x3 is equal to negative 50 x3 cubed over 3 plus 6,650 x3. Of course, that's valid on the same domain as was the shear equation. And there you go. Before we finish this, I want to just point out one little observation here. Take a look at your shear equation. Take a look at your moment equation. And one of the things that should become very clear is that if you take the moment equation and take its derivative, it will give you the shear equation. Isn't that neat? Well, that concludes this example. And as always, it's a beautiful day for studying structures.